The I-beam has a destructive history due to a little-known fatal flaw. The images you see here show ruins resulting from I-beam failures. How exactly do such failures happen? And how can such failures be prevented? In a previous video, we reviewed the secret of the IBeams Strength. Click here for a refresher on that. To summarize, the IBeams Strength comes from having more area further from the center. This makes the shape very strong in bending, which means it can take lots of downwards loads. So why then do we not take the strength of the I-beam to the extreme? When we add more and more area further and further from the center, at a certain point, the beam will buckle. Buckling can occur like this, globally, or like this, locally. One example of I-beams being taken to the extreme is something called plate girders, which are typical for highway bridges. Notice how deep the I-beams are and how they need stiffeners at regular intervals. These stiffeners are to prevent local buckling of the web. And these stiffeners, also called braces, are to prevent global buckling of the member. In these ways, buckling can be easily dealt with. However, the I-beam still has one other flawed property which causes even more problems than buckling. Until now, we've been applying downwards loads to the I-beam straight on top, in the middle of the web. However, in practice, beams can have load applied slightly off to the side. Engineers call this eccentric loading. This eccentric load causes twisting or torsion on the I-beam. The I-beam happens to be quite weak against torsional forces, but why is that? To demonstrate, let's repeat the comparison of square, eye, and circle shapes from our previous video. Again, in this example, all of these shapes have the same area and thus the same amount of material. The beams are loaded at midspan, but this time the load is eccentric. As this eccentric load increases, let's plot the stress in each of our three beams. As the load increases in each beam, the internal stress due to torsion also increases. Even though the area in each of these beams is the same, the amount of torsional stress that they take is different. As we can see in the plot, the square tube is able to withstand the highest eccentric load, aka torsion or twisting, before failure. But why is that? A beam's ability to resist torsion depends on how much continuous area exists and how far that area is from the center. These little arrows are following the path of what engineers call shear flow. The more distance that the shear flows from the center, the better the beam can resist torsion. Notice how in the solid circle, the shear flow is distributed from the center outwards and is greater further from the center. This is because the material further from the center contributes more to resisting torsion than the material near the center. And in the hollow square, all of the shear flow is far from the center in a continuous path, since all of the material is continuously far away from the center. In the I-beam, however, there is no continuous path for the shear flow other than through the center. So, the shear flow arrows are forced to move through the center. Having the area run through the center, i.e. not having a tube or hoop, restricts the I-beam's ability to resist torsion. So, the beam with the most continuous area furthest from the center will have the best ability to resist torsion. An avid watcher might ask, doesn't the corner of the square tube technically cause a discontinuity because of its sharp edge? The answer is yes, sharp corners do cause discontinuity and stresses. One way to make a beam with equivalent area even stronger than we've shown is to make a hollow, circular tube. Now this beam has the most possible continuous, smooth area as far from the center as possible.
Now, this shape is optimized for resisting torsion.
In summary, the I-beam is strong in bending from downwards loads due to more area in the flanges being further from the center. However, if the area is spread too far from the center, the I-beam can be weak in buckling. Plus, the I-beam is weak against torsion in general because it does not have continuous area far from the center. We hope this video gave you some insight into the engineering considerations that go into designing I-beams. Engineers spend unthinkable amounts of time choosing shapes and cross-sections for their beams so that failure events can be as rare as possible. Next time you're inside a building, look up and see what shapes you observe. As a growing channel, we appreciate the support of all our viewers and would be grateful if you could like and subscribe. Thank you for watching, and feel free to leave a comment if you have any feedback or would like any more information.